Hi, today I'm going to start to talk about how to calculate the wave properties from the water pressure. As you know, one of the easiest or one of the common instrument that used to to measure the wave, particularly the field, are the pressure sensor. So we can deploy the pressure sensor and it measures the water pressure, and then from that water pressure we calculate the wave properties. Uh, in case of deployment and working with the sensor, probably it's one of the most convenient one, but the problem is that obtaining the wave properties from the water pressure is not that straightforward. And the reason for that is that when we have the wave on the top of the water surface, we are going to lose the energy as we move down in the water. So let's give you some idea about what's happening. So as you know, we have this uh, bed of the sea. So and then we have the um, water surface here. This is the water surface, and then we have the wave. I just draw one wave on that water surface, so it's a water surface. And if we go ahead and say assume this and this is going to be the depth of that water surface, so it's going to be h. And we know that the effect of this wave eventually, if I draw that, um, when we move down in the water column, the effect of surface wave dissipate, attenuate in the water surface. So the energy just goes away. If it has the energy, whatever energy it has here, if we go down there, that energy keep decreasing and decreasing and decreasing, and eventually it will get to the zero. So if I let me plot it, so draw it. So eventually, if we go down to the depths that's equal to this depth is, if we have the wave length of L, if we go to the depths of that is equal to the half of the wavelength, the effect of the surface wave completely diminishes, disappears. So if we put the pressure sensor somewhere beneath that depth, somewhere here, it doesn't measure any wave. It cannot detect the wave. If we put it above that depth, if we have, for example, the pressure sensors, assume that we have the pressure sensor sitting somewhere here, it still feel and it can detect the wave, but whatever pressure is measured is way less than the pressure on the surface. So in other words, because the energy disappeared in the water column, whatever energy this pressure sensor is going to measure is less than what is actually on the water surface. So in other words, if for example, if I draw it for simple one, so if we have, assume something like that, and it's going to be the y, and it's going to be the t, and let's just draw a simple. So if this is the wave we have, or let me make it similar to the one we have there. So if this is the wave we have on the surface, then the pressure sensor most likely may depend on how deep it is going to measure something like that. So as you can see, um, its amplitude is smaller than the original one. So this is the this is what it actually is. So it's on the surface. So it's the um, surface wave, and that's the it's the actual measurement. So it's the surface, it's the actual measurement, but and this one is what the pressure sensor measure. So this is by pressure sensor. So there is an energy drop here between what is actually happening and what's pressure sensor measure. By the way, so when I say measure, so it's the we measure the pressure and then we convert it to the um, water surface. So that's what we are going to get eventually. So we have to compensate if we just get the pressure sensor data and convert it to the water depths and then calculate the wave properties from that, the results would be wrong. So we cannot just do that. And we have to fix the problem. So let's come back here, and if you assume this pressure sensor, I assume I put the pressure sensor. Um, let me erase this one. So if you have the pressure sensor sitting, for example, here, assume this is the pressure sensor we have, it sits there, and then I'm just everything is gonna measure by pressure sensor and is different from the actual value. I'm gonna gives it a prime notation. So assume this is gonna be the depths that we have. Let me choose that one. So for example, assume this is whatever it measures. So assume this is the h prime. So that's the depth or whatever pressure that measured by sensor. So and this one is the distance, and this distance is constant. I'm going to call it the ds, the distance between pressure sensor and the surface of at the bed of the water column. Now, when we have that h value here, the h value, the mean, which is the mean water depth, the h value or the mean water depth is the average. If we average this h prime, so if we say it's the mean of that h prime is equal plus that ds. So just know that if we average whatever the pressure sensor reads, converted of course to water depths. So whatever pressure sensor reads, converted to water depths, average it plus the and add it with this distance that it has from the bed. So it's going to give us the average water depths that we have here. In general, when we are dealing with the when we are dealing with the pressure depth, this is how we are going to do the calculation. So the very first thing, assume we have some measurements, and it's going to be the for example, this is T and this is the P, and then we have some measurement and it's going to be somewhere here. And remember, when we are doing the analysis, we can't do the analysis for the entire data set, so we need to split our data set into the smaller section, like into the every hour or half an hour, and then do whatever I'm gonna say that for analysis for that block of data. So make sure everything is the results correct. So assume this is, for example, is 1 hour of data. That's we have the do the measurement, and this is the pressure data we get. And then when we want to do the calculation, the very first thing we will do is that we detrend that pressure. So we'll go here and then we say, okay, that is the T and that is the P, but we detrend that. And by what I mean by detrending means just remove the mean of the data set. And the reason is that I said we have to break it down to the smaller sections that because we need it to be stationary, so we don't want to have the increasing mean or decreasing mean, so we want to have the constant mean along the section we have. So, and most of the time over half an hour or 1 hour period we don't have much change in the mean water depths, and we can assume the data set is stationary. So if I remove the mean or detrend it, that is what we're gonna get, something like that. So then the mean is gonna be 0, so from here to here, so whatever there, and then we detrend it here. So we detrend the data set, and this is what we get. And then after we got that, we will convert that to the water depths, or basically the surface elevation. And so I'm gonna call it y prime, because it's not the exact water depths, the water surface, but and then for example we change it to whatever it's gonna be, and to do that we divide everything by rho g, which the rho is the density of water and g is 9.81 with gravity acceleration. So we divide the pressure value by rho g, and it gives us the water surface elevation, or the wave data. The only problem with this wave data is that, as I mentioned before, we lost some energy when we measured the p-values, and because we lost some energy here, this water elevation that we get here, this wave data that we get here, is smaller than the actual waves that how the wave actually was. When we get to this point, we have two ways of doing the calculation. One way of that to do in the spectral analysis and correct the wave data, and the other ones that are using the zero crossing and correct the wave data. So first I will talk about the spectral analysis, and then I will explain the zero crossing. If we want to do the spectral analysis, so what we will do that is we go ahead and we say that we have the y prime, and then we calculate. So we calculate the spectrum of that y prime. So here from the pressure we can't always get to the y prime, and so we have the y prime, and from the y prime we will calculate the power spectrum of that wave data that we have. And then to get the power spectrum of the correct wave surface elevation, to compensate for the energy we lost, we divide as y prime by pressure response factor squared. So if you look at it, it's not that difficult. So we have this data, can easily calculate the spectrum of the this data, and then this is just a number. We can divide that one to get the corrected spectrum. So this spectrum is from the wave data that has some energy attenuation, as it has lost some energy, and then here is the actual spectrum. So here we compensate for the energy that is lost in the water column, and the Kp, if you want to calculate the Kp, is just as the cosine hyperbolic of the KdS So the k ds divided by cosine hyperbolic of k h. And the ds, as I said, is the distance from the pressure sensor to the bed, and h is the mean water depth. The k is the wave number, and this k is a function of the frequency, is function of the wave frequency, and because of that, this kp is also going to come out as a function of frequency. So, and it can be calculated mathematically relatively easy. So if you can see, it mathematically doesn't have much difficulty. It can be done easily, but it's harder to do when actually want to do the calculation. And to show you why it's that, let me show you what's happening. Um, So to show why, how we do the calculation in the real one, I'm gonna give you some examples. So assume that we have, and draw everything in the logarithmic scale because it's easier to follow. But if we have the f and we have the s y prime y prime, and this is going to be in hertz, and it's going to be meter squared in hertz. Then if I draw it in the logarithmic scale, it's gonna look like something like this. In logarithmic space, that spectrum is gonna look like something like that. Now if I draw the kp value respect to the f, and it's going to be the kp, the pressure response factor, then the pressure response factor is going to be look something like this. And it's going to be 1 here, and it goes so it's going to be 1 at this point, and eventually it goes to 0. Now if I divide, and as remember I said that to get the syy, I have to divide sy prime y prime by kp squared. So if I start to divide that, because this is always smaller than 1, so if I just divide it by that, it's gonna, the syy is going to be always larger than syy prime, because the kp, as you see, is always smaller than 1. So if I go ahead and do that and draw that, and here is 1, so whatever I'm gonna draw the syy prime. So what we're gonna get is very close to what we have originally, and then slowly we will get increasing in value, so we're gonna have the larger value, and it comes all down, and then it gets to the point that because the kp becomes so small and very close to 0, it causes that when we divide the syy by that, it causes it just start to go toward infinity. So this is syy, and this is syy prime. And let me just delete these prime. So it's a spectrum. Anyway, And if we do that, it goes toward the infinity, and whatever we get is going to be wrong. Um, so to prevent such a things happen, we cannot just simply divide it by kp. We have to find some places and then stop at that point. Um, in my experience, and this is just my experience, I don't have any specific um, explanation why it's working. What I myself was doing is that I will come here. When I would do that, I try, when I divide it by kp, I try to find this point, the minimum point here, when it actually it starts to deflect and goes up. And whatever kp I have at that point, I apply that kp for the rest of the spectrum. So instead of having the k, for example, if I go all the way down here, whatever kp I have at that point, I use that kp for the rest of for the higher frequency. And as a result, instead of it shoots up, it will uh, goes like this, because it's going to be constant, so it goes like that. So it's going to be my spectrum, and then I don't have this shooting part that it goes up. Um, so it will be something like that. Instead of going up, it goes down. So basically, I apply the kp up to this point, and by the time I get to this point, I apply the constant kp afterward. I'm not using the kp from this chart anymore. It's not that easy to do that when you do the programming, because it might, when you go there, that points might be moving back and forth between every every spectrum. So any new spectrum you have, it might be a little bit toward the left or a little bit toward the right. So you have to write the code that actually go and find that point, and then from that point you apply the constant kp factor, just to prevent this from happening. This is how we are doing it if we have the spectral analysis. If you want to do it in, let's say, if you want to do that in zero crossing, there's another way that we have to do that. So remember I said we eventually, when we go ahead and calculate, we find the we have the pressure data, then from the pressure we get the trend, the pressure data, and then from there we get the y prime data. So assume I just exaggerate one, so assume these are the y prime data, and we want to calculate the y from this. So assume that's what we have. And so that's assume this is our the R waves data set that we have. So to do that, when we want to calculate that, in this case, when we have it, we will go ahead and find the y is equal actually to our y prime divided by the kp. Now we know how to calculate the kp, but we have to find the kp for each of these waves. So what we will do, that we will go ahead and find the very first wave, which is going to be from here to here. So this is going to be our first wave. So from here to here is our first wave. So we get, okay, this is our first wave. So if this is a t, then this is the period for the first wave, and from the period for the first wave we can find the frequency for that, and then we can find the kp for that wave. And then when we find the kp for that wave, we will go ahead and divide all the data points in that wave by that kp. Then we will move to the second wave and we'll find the second wave, which is going to be from here to here. So we'll say, okay, this is our second wave. So it has a T2, the period of that, and then the frequency of that, and then the Kp for that wave, and then divide all the data points for that wave by that Kp. And then we move to the third one, which is going to be this one. So it has a period, of T3, and then its frequency, and then its Kp value, and then every data set we have in that wave will be divided by that Kp. And by doing that, we will uh, correct the wave data wave by wave. So we get every wave, single wave, every single wave, and we do that, and we go ahead and we fix the uh, um, data. Here, similar to what we have in previous section, if we have the very small Kp, then we are going to have the artificially large y value, which is going to be again wrong. So we have to um, limit the lower value of the Kp. So most of the time I would probably, I myself, I would say that, and again, I don't have any specific reason for that. I find that it works. So I will say the minimum value that the Kp can have is 0.15. So if it's less than 0.15, when I calculate the Kp, it's become less than 0.55. I limit it to that value to make sure it's not going to get smaller than that. And by the time when I finish all, I have all the corrected wave, then I can do the analysis on that to get the corrected wave properties. Uh, most of the time I've seen the zero crossing method is way harder to do than the let's say spectral analysis, because you have to go ahead and just find every single wave and do it for that. But because we are actually bringing out every single wave, it's less likely to make a mistake, and the results are most of the time seen the results very good and acceptable. Anyway, either way that we will decide to go, we can do that with the spectral analysis or with the zero crossing method to compensate for the energy loss in the water depths if we use the pressure sensor to measure the water depths, and that is basically how we do that.